Welcome to ECE 302. This is lecture 4.2 on expectations for continuous random variables. I'm Professor Stanley Chan. So let us recap from the previous lecture. This is the diagram we want you to remember. In the past, when we talk about discrete random variables, we have this probability mass function. And then they are just impulses on a finite number of states. When we go to the continuous random variable, we change the probability mass function to the probability density function. It is a continuous curve, and if we want to calculate the probability over an event A, we need to integrate the area under the curve. So today's lecture, we are going to look at expectation, or in other words, how do we calculate the mean of a random variable. Now you can see that the idea will be pretty straightforward going from the discrete case to the continuous case. In the discrete case, we count this state, and then we count how many samples are there. We sum them up with this state multiplied with this height. So you can imagine that for the continuous random variable, we'll be doing something similar. We look at this state, we multiply with this height, we go to another state, we multiply with this height, and then we just integrate over the entire region dx. Then we will be able to get the expectation. So this is a very, very quick intuition about how do we do expectation for continuous random variables. Now, this is the outline of today's lecture. We're going to talk about expectation. We're going to talk about the properties. Both are exclusively for continuous random variables. Then we want to comment on a small thing, which is the existence of expectations. And afterwards, we will talk about moments and variance. So what is the definition of expectation? The definition is given by this formula. It is the integration of fx multiplied with x, and then you do this dx. So how do we understand this? As I have shown in the previous slide, let's say we have a function fx. This is the probability density function associated with a random variable x. Now, this fx is here. And then what would be the state? Here is the state, okay? So let's say I have a value x, and then I go up to my probability density function, and then I find the height. So this is fx at a value x. Here is, let's say this is x, this is x prime. This is fx evaluated at x prime, okay? These are the height times the state. And then how are we going to do? We are going to integrate this x, which is this value here, times your height fx, and then dx. And integrate over all the possible states that you have. This is more or less equivalent to the summation of your x times px of x, where x will be summed over all the possible states in the sample space. So this is just a continuous version of the discrete expectation, and you can see that they are very, very similar. It won't be clear until we work out some examples. So here is the first example. Suppose I have a PDF fx, which is defined as this constant 1 over b minus a for the range x being between a and b, 0 otherwise. We want to find the expectation of x. So the expectation of x, according to our definition, is just the integration of x, fx, dx. X is going from a to b. Now, what is this fx? This fx, in our case, it would just be 1 over b minus a, okay? And so that will give me this integration of a to b of x dx, and then this 1 over b minus a is a constant, so we can pull it out. And then I can do this integration. This integration will give me x squared divided by 2, evaluate from a to b, and then I also have 1 over b minus a. Okay, and so now if you evaluate this integral, that will give you 1 over b minus a times 1/2 of b squared minus a squared. So what is this? This is b minus a times b plus a divided by 2 times b minus a. So we can have a cancellation. So that will give you b plus a divided by 2. Okay, and this is the final answer to this expectation. Okay. Now, does it make sense? Well, it makes a lot of sense if you draw the diagram. Here is your fx. Fx is a uniform distribution from a to b with a height of b minus a. And then what is the mean? The mean, according to this formula, it is at the center, which is b plus a divided by 2. Okay, so the mean is right here. Let's work on another problem. Here is the PDF of an exponential random variable. In this case, fx is equal to this lambda times e to the power minus lambda x. The expectation of x is just the integration of x times fx dx. And in our case, this fx is lambda e minus lambda x. So we can plug it in. So we have integration from 0 to infinity, because that's the range. Okay, so 0 to infinity, lambda x, e minus lambda x, and dx. Okay, now how do we do this calculation? Well, this calculation can be done by using a trick called the integration by part. Okay, how do we do that? So this is equal to x d of e minus lambda x. Okay, don't forget that there's a minus sign here. Now, okay, and then how do we do it? We can switch the row, so you have a x e minus lambda x going from 0 to infinity, and then you have minus, there's a minus here, and then there's a plus, integration from 0 to infinity of e minus lambda x and then dx. So the first integral will give you what? The first integral will give you, you need to evaluate this thing at infinity, which will give you 0, or you evaluate this at 0, so that will give you also a 0, so that the entire thing will give you 0. And then you calculate the second integral. The second integral is just the integration of e minus lambda x, so that will give you 1 over lambda minus, and then e minus lambda x, you evaluate from 0 to infinity. That will give you 1 over lambda, because that constant is just, that will give you 1. Okay, and so we have shown that the expectation of this random variable x is 1 over lambda. So you can see that the whole trick, the most important thing, is to calculate this integration. The rest is just a simple calculus. Now, if you have a function g, okay, and then you apply this function to x, then how do we calculate the expectation? It turns out that the expectation of gx is just this integration of gx times fx dx. Now, why is it the case? You can think of that there is a function g, and then you have a random variable x. After this transformation, you will go to this gx over here. Now, the probability of getting these states are remaining unchanged. Okay, so let's say here you have x1, x2, and x3. Then you have gx1, gx2, and gx3. The probability of getting these, they are the same as probability of getting these. Okay, and therefore, if you try to calculate the probability, the expectation of these guys, when you go through this transformation, it will be these state values times their respective probabilities, which is this equation. These are the state values times the probability. You integrate, then that will give you the expectation. So let's work out an example again. So here is this uniform distribution, and then now we want to calculate this x squared. So the expectation of x squared, according to our definition, it will be integration of x squared times your fx dx, integration from a to b. Now, what is this fx? Again, this fx is 1 over b minus a. Okay, so now you plug this number in, b minus a, you integrate from a to b of x squared dx. How do we calculate this integration? That's just calculus. So we know that this is 1/3 x to the power 3, evaluating from a to b. So that will give you 1 over b minus a times, this is 1/3. You have b the cube minus a the cube. And then you can do a simplification. You have a 3 in the denominator, and then you have a b squared plus ab plus a squared in the numerator. And that is the solution to this expectation. All right. So again, the key is to recognize this definition, which is that when you have any function g applied to your random variable, then you apply this g inside this integration. Now let's work on a little bit more difficult problem. Here is the PDF of a random variable theta, and theta is 1 over 2 pi with this range. And we want to calculate this expectation of y, where y is cosine omega t plus this theta. Okay, so we ask, okay, what is the expectation? Okay, so expectation of y is the integration. All right, and then now what is the function? The function is cosine omega t plus theta, and then you have f of theta, d theta. Theta will go from 0 to 2 pi. Okay, you see that this is just that function, and that is the probability density function. And this probability density function is 1 over 2 pi, and that's just a cosine function. So we can evaluate that. So you're integrating from 0 to 2 pi, cosine of omega t plus theta, d theta, 1 over 2 pi. Now, at this point, you may be a little bit confused about this integration. So whenever you're confused, don't be confused. Just replace this omega t by your favorite smiley face. Okay. Now, why do I do that? It's because this omega t has nothing to do with your integration variable theta. Okay. And a lot of times, some students will try to integrate with respect to t. Now, don't do that, because the variable that you're trying to integrate is with respect to theta. And that's why I'm drawing a smiley face here, to make sure that we are not integrating with respect to this smiley face. We're integrating with respect to this theta. Now, if you integrate with respect to this theta, what do you see? Well, we can draw a diagram to see what is going on here. Here you have a cosine function. So this is a cosine function. Now, a cosine function from 0 to 2 pi, what do you get? Well, from 0 to 2 pi, you integrate this function. This entire thing will give you 0. Okay. Now, what happens to when you have a smiley face? When you have a smiley face, it doesn't really matter. It just offsets this x by this smiley face. So it doesn't matter. You still integrate this function from 0 to 2 pi. You will still get 0. Okay. So the answer 0 is the expectation of this random variable y. Now, here is the third example. The example says that I have an event A inside the sample space omega, and I'm defining this function IA of x is an indicator function. So if your random variable x is inside the set A, then that thing, let me call it y, okay? Y will give you value 1. If it's not, then y will give you value of 0. So we want to find expectation of y, or in this case, expectation of this indicator function A. So what is this expectation? Well, this is the integration of this indicator A of x, and then you have fx dx. Okay. Now, this is integrating over all the possible x, so you have integration over the entire sample space omega. Now, what do? Well, this indicator function will give you either 0 or 1. Okay. So you can break it up into two parts. One is that x is inside A. Now, if that happens, then this indicator function will give you 1. And then you have fx dx. Otherwise, you have x is not in A. Then this indicator function will give you 0. And then you have fx dx. Okay, so the second one, this integration, of course, is just 0 because you have a 0 here. This one is what? This one is just integration of x inside the set A of fx dx. And this is precisely the probability of getting an A. Okay, and so this result says that expectation of the indicator function of A of x, where x is being inside the set A, is just the probability of A. This is a pretty useful result when you try to analyze certain events. Now let's talk about a few properties of the expectations. And these properties are not new. Okay, when we talk about discrete random variables, we have already talked about these properties. Property number 1 says that if you have a constant A, you multiply with a random variable x, the expectation will be applied to x only, the A can come out. Here it says that when you have a random variable x, you add with a constant A, the A will just come out because it's a constant with respect to the expectation. 3, it says that you have ax plus b, then A will come out, b will come out. That will give you this linear transformation of a random variable. Now let us talk about a subtle thing. Okay, this is called the existence of expectation. A random variable x is not always guaranteed to have expectation. A expectation exists only when the random variable is absolutely integrable. What it means is that if you take this integration of the absolute value of x, you multiply with fx, which is also the expectation of absolute x. If this is less than infinity, then we call that the random variable is absolutely integrable. Random variables that are absolutely integrable will have expectations. Random variables that are not absolutely integrable, they do not have expectations. For example, a Cauchy random variable with this PDF, it does not have an expectation. Okay, we can show pretty easily that if you have the expectation of the absolute value of x, essentially you're taking this integration from minus infinity to infinity. That's the range of your Cauchy random variable. And then you have this absolute of x, and this is your fx. You integrate that, and because this is an even function, you can just evaluate the 2 times of the integral from 0 to infinity. Now, what is this integral from 0 to infinity of this function? You can look up some integration table. That will give you half of the log of 1 plus x squared. And if you evaluate from 0 to infinity, that will give you infinity. So that means your random variable x is not absolutely integrable, and therefore expectation of x does not exist. You can actually do this calculation by yourself, and you can show that expectation of x is indeed infinity. It is not defined. So finally, I want to comment on the moment and variance of a continuous random variable. This definition of kth moment is just expectation of x to the power k, and this is following directly from the expectation of a gx, where your g in this case is just the argument takes the power to the power k. The variance of the continuous random variable is defined as the expectation of x minus mu square, where mu is the expectation of x. And we can easily show the following result, where the variance of x is equal to the expectation of x squared minus mu square. And this is also true for continuous and also discrete random variables. Now, let us work on example. Here is the discrete random is a uniform random variable with this fx 1 over b minus a for range of x being between 0, a and b, we want to find the variance of x. Okay, and in the previous slides, we have already shown that the expectation of x is a plus b divided by 2, and then the second moment is a squared plus ab plus b squared divided by 3. And so we ask, what is the variance of x? And then we know that variance of x is expectation of x squared minus mu squared. And so that will give us a squared plus ab plus b squared divided by 3 minus a plus b divided by 2 square. And then you can do some calculation. Then you will see that this is equal to b minus a squared divided by 12. Okay, so you can show that the variance of expectation of this random variable x is b minus a squared divided by 12. So here is the summary of today's lecture. We have gone through a couple of topics in expectation. We have defined the expectation of continuous random variables, which is according to this formula. If we have a function on the random variable, then the expectation can be just carried out in the same way as we were talking about the discrete random variables. There are three properties associated with the expectations. Where you have a constant a, you multiply, you add, or you have a combination of multiply and add, all these constants will come out. The existence of the expectation is guaranteed when the expectation of the absolute of the random variable is finite. This is also called the absolutely integrable property of the random variable. And finally, we define moment and variance. In particular, I encourage you to remember this result, that the variance of x is equal to the second moment minus the first moment squared. So this is the end of today's lecture. I hope you have learned something. If you have any question, please let us know. Please post your question on Piazza. Please also try our homework problems. A lot of details of this lecture can be found in the ebook. Please take a look. Thank you very much.